In this example, we have a roller coaster that's sitting at rest on top of a 113-meter high hill. It's going to roll down to the bottom of a 22-meter hill, and then it's going to roll up again to the top of a 67-meter hill. And the question is, what's the speed at the bottom of the hill, and then what's the speed at the top of that 67-meter hill? Now, the only way we can solve this problem is to think about the energy involved. While it's at the top of the hill, the roller coaster has potential energy. Its potential energy is given by mgh. Well, we don't know the mass, but we do know g, it's 9.8 meters per second squared, and we do know the height, 113 meters. So that's an equation for the potential energy of the roller coaster while it sits at the top of the hill. What about the kinetic energy? Well, the kinetic energy of the roller coaster at that point is 0 because it is at rest. So what's the total energy then? Well, if the kinetic energy is 0, then the total energy is just the potential energy. So the total energy is also m times 9.8 meters per second squared times 113 meters. Now this is very important. This is an expression for the total energy. No matter what, this expression cannot change. So no matter where the roller coaster is in its journey, its total energy is always given by this equation. This equation is so important then, I'm going to erase it here and I'm going to put it back at the top of the board to indicate just how important this equation is. Alright then, so that's an expression for the total energy of the roller coaster everywhere on its journey. Well, let's see what happens when the roller coaster goes to the bottom of the hill. Its total energy is still given by the expression we've got there, but now its potential energy has changed. Once again, potential energy is given by mgh, but now potential energy is m, we still don't know m, times g, 9.8 meters per second squared, times h, which is now 22 meters. So now that's the expression for potential energy. Well, the roller coaster is obviously moving, so it also has kinetic energy. Kinetic energy is given by 1/2 mv squared, and right now that's the best we can do because we don't know either m or v. So we just have that kinetic energy is 1/2 mv squared. Now the total energy is the sum of kinetic plus potential. So the total energy is the potential energy, m times 9.8 meters per second squared times 22 meters, plus the kinetic energy, 1/2 mv squared. Now at this point you might think we don't have much, but we really have everything we need to solve the problem. You see, here is an equation that represents the total energy of the roller coaster. However, here is another equation that also represents the total energy of the roller coaster. The total energy cannot change, so these two expressions have to be equal to one another. That's the key to solving these kinds of problems. Develop expressions for total energy. And if you've got the total energy at one point and the total energy at another point, you know those expressions have to equal each other. So the two expressions I have in blue there have to be equal to each other because they both represent the total energy of the roller coaster, and that is not allowed to change. Well, let's set them equal to each other then. Let's take the top expression, n times 9.8 meters per second squared times 113 meters, and set it equal to the expression we just developed. Now, unfortunately, the board is not wide enough, so I'm going to have to continue this on the next line. But that expression there equals the expression we just developed, m times 9.8 meters per second squared times 22 meters plus 1/2 mv squared. Now look what happens. The mass cancels. You see, mass is in every term on both sides of this equation, so it cancels out. When mass cancels, there's only one term we don't know, the speed, v. We can solve for that. I'm not going to go through the algebra here, but if you do the algebra, the solution is v equals the square root of 2 times 890 meters squared per second squared. When you work that out, you find out that v is 42 meters per second. So, at the bottom of the hill, the roller coaster will be traveling with a speed of 42 meters per second. Now, I'm not going to answer the second part of this question, what's the speed at the top of the next hill, because it uses exactly the same reasoning. We have that expression for total energy that's still there right under the drawing of the roller coaster. That expression is always true. When you put the roller coaster on top of the second hill, you'll develop another expression for its total energy, potential plus kinetic, and you'll set that expression equal to the total energy expression that's still written up there right under the drawing of the roller coaster. Once again, you'll see that mass cancels, and the only thing you have to solve for is v. Like I said, I'm not going to go through this because it's basically the same thing.